I now want to start with a very general initial condition of an object, little m, in orbit, in an elliptical orbit, and I want to see how we can get all the information about the ellipse that we would like to find out. So I'm only giving you the initial conditions. So here is an ellipse, here is P and here is A. If this is an ellipse around the Earth, then this would be perigee and this would be apogee. The mass is capital M. This is point Q. Let me get a ruler so that I can draw some nice lines. So the distance AP equals 2a, a being the semi-major axis, and our object happens to be here, mass little m, and this distance equals r0. Think of it as being time 0. And at time 0, when it is there, it has a velocity in that ellipse. Let this be v0, and there is an angle between the position vector and v0. I call that phi 0. So I'm giving you n, I'm giving you v0, I'm giving you r0, I'm giving you phi 0. And now I'm going to ask you, can we find out from these initial conditions how long it takes for this object to go around? Can we find out what QP is? Can we find out what the semi-major axis is? Can we find out what the velocity is at point P at closest approach when this angle is 90 degrees? And can we find out what the velocity is when the object, when little m is farthest away, apogee? Can we find all these things? And the answer is yes. A is the easiest to find, the semi-major axis. I turn to equation number 5, which is the conservation of mechanical energy. And the conservation of mechanical energy says that the total energy is the kinetic energy plus the potential energy equals 1/2 m v0 squared. That is when the object is here at location D, minus little m, capital M, G, divided by this R0 at location D. This can never change. This is the same throughout the whole orbit. So it must also be, according to equation 5, minus mm G divided by 2a. And so you have one equation with one unknown, which is a. Because you know all the other things, m cancels. M always cancels when you deal with gravity. So you only have a as an unknown. So that's done. If the total energy were positive, then for this to be positive, a has to be negative. That's physical nonsense, of course. So this only holds for bound orbits. So positive values for E total are not allowed. Once you have a, you use, so this is from equation number 5. If you now apply equation number 6, immediately pops out t, the orbital periods. Because the only thing you didn't know yet was a, but you know a now. So we also know how long it takes for the object to go around in orbit. And I try to be quantitative with you. Step by step, as we analyze this further, I will apply this to a specific case for someone going around the Earth. Everything I'm telling you today, including all numerical examples, are in a handout which is 6 pages thick, which I wrote specially for you. It will be on the web. We're not going to print it here. That's a waste of paper. It's $19.99, so that's what we have the web for. So you can decide on your own how much notes, how much time you want to spend on notes, or to what extent you want to concentrate and try to follow the steps. It's up to you. But everything is there. Literally everything. Every numerical example. We take for capital M, we take the Earth. And that is 6 times 10 to the 24 kilograms. So that's my M. I promise you, you will know M. I will give you R0. That is 9,000 kilometers. That's the location at point D. I give you the conditions at D. The speed at point D is 9.0 kilometers per second. And I'll give you phi 0 is 120 degrees. Everything else we should be able to calculate now from these numbers. First of all, with equation 5, you can convince yourself, sticking in these numbers, that the total energy is indeed negative. Of course, if I make the total energy positive, it's not an ellipse. So then it's all over. It is negative, it is an ellipse. So with equation number 5, I then pop out A. Right? Because that's one equation with one unknown. And I put in the numbers. You can confirm them and check them at home. And I find that A is quite large. A is about 50,000 kilometers. That's huge. That is almost infinity, not quite. Remember, it starts off at 9,000 kilometers, but A is 50,000 kilometers. That means 2A is 100,000 kilometers. Why is that so large? Well, the answer lies in evaluating the escape velocity. The escape velocity of this little mass, when it is at position D, for which these are the input parameters, is the square root of 2mg divided by R0. And that is 9.4 kilometers per second. Well, if you need 9.4 kilometers per second to make it out to infinity, and you have 9 kilometers per second, you're pretty close already. So that's the reason why this semi-major axis is indeed such a horrendous number. It's no surprise. If now I use equation number 6, then I find the period, and I find that it takes about 31 hours for this object to go around the Earth. So far, so good. Now we want to know what the situation is with perigee and with apogee. Can we calculate the distance QP? Can we calculate the speed at location P and at location A? And now comes our superior knowledge. Now we're going to apply for the first time in systems like this the conservation of angular momentum. Angular momentum is conserved about this point Q, but only about that point Q. It is not conserved about any other point, but that's okay. All I want is that point Q. That is where capital M is located. What is the magnitude of that angular momentum? Well, let's first take point D. When the object is at D, the magnitude of the angular momentum is m times v0 times r0 times the sine of phi 0. This is the situation at D. Why do we have a sine phi 0? Because we have a cross between r and v, and with a cross product you have the sine of the angle. So that's the situation at point D. What is the situation at point P? Well, at point P, the velocity vector is perpendicular to the line QP. So the sine of that angle is 1. So now I simply get m times v of p times the distance QP. And you can do the same for point A. You can write down m times v of a times qa. I'm not doing that, and you will see shortly why I'm not doing that. Nature is very kind. Nature is going to give me that last part for free. This, by the way, is the conservation of angular momentum about that point Q where the mass is located. I have here one equation with two unknowns, v of p and qp, so I can't solve. So I need another equation. Well, of course, there is another one. We have also the conservation of mechanical energy. So now we can say that the total energy must be conserved, and the total energy is 1/2, I do it at point P, equals 1/2 m Vp squared, that is the kinetic energy, minus mmg divided by the distance qp. This is the potential energy when the distance between capital M and little m is QP. But this number we know because that is minus mg divided by 2a. That's our equation number 5. Oops, I slipped up here. You may have noticed it. I dropped a little m, which should be in here. Sorry for that. And so now we have here a big moment in our life that we have applied both laws. This is the conservation of mechanical energy. And now I have two equations with two unknowns, QP and V of P. And so I can solve for both. Notice that this second equation is a quadratic equation in V of P. So you're going to get two solutions. And the two solutions, one V of P will give you the distance QP. The other one will be VA, which gives you the distance QA. How come that we get both solutions? Well, this is only a stupid equation. This equation doesn't know that I used a subscript P. I could have used a subscript A here and put in here QA. That's the term that I left out. And therefore, when I solve the equations, I get both VP and VA because those are the situations that the velocity vector is perpendicular to the position vector.